Hey guys, it's me again, coming at you from Madison, Wisconsin. This here is a problem that deals with wave intensity and relates it to power. So we have that a TV remote produces a 250 milliwatt signal. The receiver unit will respond to a radio wave of correct frequency if the electric field amplitude exceeds 0.1 volts per meter. What is the max distance your remote can work from? And then it tells us to assume essentially that the transmitter radiates uniformly in all directions. And this is an important consideration because this is going to tell us what this area is. So intensity can be uh, solved for essentially if you know uh, basically if you can fill in one of two equations. The first one you can see here relates power and area to intensity, and essentially the intensity is the power divided by the area, and that makes sense because it's basically the sort of intensity you can think of as being the density of the power in some ways. But intensity can also be given by this expression, which is sort of cumbersome. And you'll note that it has both the speed of light given there by c, the symbol c, and then it also has one of the great, I think, one of the best named constants in science, and that is the permittivity of free space. And that's sort of well, I'll get to it in a second. It's also a very cumbersome constant here. You can see it has coulombs squared over newtons times meters squared, but it's given by this value. And so I won't get into what that is today, but just know that it's related to the intensity. And so to solve this problem, what we're looking for is the max distance from which the remote can work from. To solve this problem, we want to relate these two equations to each other. So simply we can just set up power over area equals, speed of light, by the way, is 3 times 10 raised to the 8th meters per second. And we have the speed of light times permittivity of free space times E max squared. And E max squared, or I should just say E max, is this value, volts per meter, the electric field amplitude. So now we can just plug in all these values, the ones we know, constants first because those are the easiest. So we'll say 3 speed of light, 3 times 10, raised to the 8th meters per second. Plug in the permittivity of free space. That's this guy. Coulomb squared times Newton or divided by newtons over meters squared. And then this is all over 2. And by the way, multiplied by 0.1 squared. I'm not going to include the units here just because I'm running out of space. But all this is equal to power over area. Now, we were given the power. We were given the power up here. It's 250 milliwatts. So basically, you can just think 2,000 or 250 times 10 to the negative 3. But area, well, you might say, well, we don't know that. But at the same time, that's not what we're looking for, right? We're looking for distance. Well, this, what I have starred here, tells us what the area is, because it radiates uniformly in all directions. Directions, what the fuck? Sorry. I should say directions. We know that this is the area of a sphere. And the area of a sphere is 4 pi r squared. So, I'm going to go back. I'm actually just going to rewrite this as 250 times 10 raised to the minus 3 watts. Because remember, we had this in milliwatts initially. And then 4 pi r squared. And as it turns out, the radius of that sphere is the distance, or the max distance, I should say, that the TV remote will work from. So this is a little bit of a cumbersome problem, but now that we have all the pieces, we can go about solving for r. So, just going to rewrite this here. 50, be quick about it. And I'm going to leave out the units. Just so that we have enough space. Oops. Oops. So, now, just going to do a little rearranging here. I'm going to move r squared over, because r is what we're solving for. And then, what I'm going to do is I'm going to get everything else on one side. So I'm going to get 2 times 250 times 10 to the minus 3. And this is all going to be over 4 pi times 0.1 squared times 3 times 10 to the 8th times 8.85 times 10 to the minus 12. And then you can see I can actually go one step further, hopefully, if this makes sense to you. I'm going to erase r there. And actually, just by taking the square root of both sides, I get r alone is equal to the square root of this. So, if I do this in my head really quick, let's see, yeah, carry the 1, let's see, it's going to be like 1,000,000 divided by 2,000,000, okay, okay, hold on, yeah, and, do this, and then just like that, okay, makes sense, yeah, okay, and then, yeah, okay, makes a lot of sense, yeah, and, invent a number, okay, it's imaginary, okay, now, add it to 1, let's see, okay, get this, and then, yeah, so after doing that in my head, basically what I get is 38.7 meters. If you heard the sounds of a calculator, I don't know, that was someone else working next to me. So, I'm going to go back up to the top here just to explain what happened and what we were solving for once again. So, we were looking for the max distance that the remote would work from. And so, we related these two equations with each other because they're both equal to the intensity. And so you kind of just had to know that in order to solve this problem, at least in this way. And then, because we knew that the transmitter radiated uniformly in all directions, we could deduce that the area was the area of a sphere, 4 pi times the radius of the sphere squared. And then we were able to figure out that what we were solving for, the distance, was the radius of that sphere. And so, using some math, we were able to equate these two expressions to one another and then solve for r. So, the remote works at 38.7 meters away. If you get any further away, it doesn't work. If you move closer, it still works, so great. All right, so that was a wave intensity problem. Again, that's kind of a tough problem, but it's a good one because it makes use of a lot of different things. So if you have any questions, if you saw that anything was wrong, get in touch with me. Otherwise, until next time, thank you.